Vectors in 3D. Pretty much everything you did with vectors in two-dimensional space, that would be a flat plane, you can do with vectors in three-dimensional space. Okay, so all your general calculations, calculating magnitude, doing dot products, adding vectors, figuring out resultants, all that business, you can do that in three-dimensional space. Application problems, you might not be able to look at the navigation of a ship in three-dimensional space. That probably wouldn't apply, but you could maybe think of an airplane that's not flying parallel to the ground, and that would give you a three-dimensional movement. All right, so to get things started here, what we need to do is get a concept of how we're going to, I guess, quantify the three-dimensional space that we have. So to do that, we're going to add in another variable, like another direction that we can have. So you're used to the x and the y. Okay, x is left, right, y is up and down. We're going to add in another component, which is going to be the z component, and you can consider that like a depth component. Okay, so the picture that I have here, actually, before I start, what I want to do is make a point that this is a picture on a two-dimensional plane because it's a flat piece of paper. And our attempt here is to draw a picture that's in three-dimensional space. So there's going to be a little bit of an oddity to that. Okay, that depth direction is going to be a little bit weird to interpret if we're trying to put this on a flat piece of paper. We're trying to draw 3D in 2D space. Okay, but these axes here, these two, just for the sake of consistency, this is going to be my x-axis. Okay, so that'll make this the origin over here. This is the x-axis in a positive direction. This is going to be my y-axis in a positive direction, so that we keep those things consistent. There are other diagrams out there where the axes will get moved to different positions or different orientations, the way that you'll look at them. This is the typical one that I will use. The third axis is going to be called the z-axis. That's going to give you a depth. Okay, so think of this as the origin. Positive x's that direction, negative x's that way, positive y's, negative y's. Then for the z, moving out to the front is going to be a positive z direction. Okay, so it's sort of coming outside of the paper. Okay, we're going to draw it at an angle to give it some three-dimensional look to it. Okay, but that part does get a little bit confusing because you can't use these lines as increments. You may just need to add on your own. In order to help you visualize this in three-dimensional space, what I'm going to do is draw a rectangular prism. I think that will really bring out this 3D idea. Okay, so I'm going to identify a point which is just going to be vaguely called x, y, z. So it has some x value, some y value, some z value. And for simplicity here, they're all going to be positive numbers. Okay, so I'm going to choose pretty much a random x just over here. So that would be 5 units over, but it doesn't really matter for what I'm really trying to accomplish here. Okay, but that would be the x. The y value, again, I'll just choose something positive. So I'm choosing at a 3. Doesn't really matter what it is, I just want to mark off a spot. Okay, and then along the z-axis, really choose a random location. I did mention that you might want to just add your own little lines in there, so I'll go ahead and do that. So you can see that it's not really intended to match the background grid. The background grid is really for the x and the y's that are here. All right, so given these 3 coordinates, I'm going to draw a rectangular prism that would sit sort of like in a corner here. Okay, so this is going to be the back side of it. That'd be the back. All right, and then from this point up, which I have just a little bit off of that line, I'm going to go up 3 units, which, the way that I did this, I might just need to measure it here. Let's see if centimeters would probably work better. Okay, the length of that is about 2.1, so I'm just going to go 2.1 here. And that z-axis locations are a little bit odd. Okay, so then I should be able to close this off, and that'll appear parallel to that. Okay, and then we're sort of going to need to do the same thing across the bottom here. Take a measurement. What is that, about 3.7? I think that's there. Okay, doesn't have to be perfect, but we'll aim to make it look reasonable. All right, so I got the back side, I got the left side here, and then what would be the bottom. So now I'm just going to Let's see, that measures pretty much just right up to a line. So I'm going to match that up to build the front. Then I can close this guy off right here. Okay, and I believe I got all the pieces there, and that should start to look like a rectangular prism sitting like in the corner maybe of a room that we'd have there. All right, now this is the point B that I wanted. All right, so to get to point B, what you would need to do is measure out X units, that direction, which seems to go past B, but then you're gonna go up Y units, and after that, you're gonna move forward to get to that location right there. Okay, so B is just a point that's floating out there in space, and if I were to connect the origin, that's what I'm referring to here as O, if I connect the origin to B, then that would represent a vector in three-dimensional space, okay? But now imagine for a moment that we didn't have that prism that was drawn there. So I think the prism helps us see that we're coming from that back corner to the front corner. We can visualize that. But if you didn't have the prism, what it would really look like is just a vector that would be sitting on that back grid that would be going over 3 and up, well, 3 and a little bit, and then up 2 units there. Okay, so the prism's really gonna help out. You're not gonna draw the prism for every single diagram that you have here, but you sort of wanna keep it in mind that these vectors, we're trying to draw them in three-dimensional space, but in a two-dimensional plane, they might not come across as clear as we really want them to be. All right, for the rest of the video, what we're really gonna do is demonstrate that any calculations that we do with vectors in two-dimensional space, you can do with vectors in three-dimensional space. And we're gonna start by looking at magnitude. So recall that these bars here would indicate that we're looking to calculate the magnitude for the vector that would run from O to B. Okay, trying to figure out what the length of this would be here. And to do that, in two-dimensional space, what we did is use Pythagorean theorem. We took x squared plus y squared and then square rooted it. Basically, we took our horizontal component, we squared that, we took our vertical component, squared it, and then square rooted to get the length of that diagonal. In three-dimensional space, you will still use Pythagorean theorem, but it's going to be a modified version that brings in the third component squared as well. All right, for example 1, we're given 2 points A and B in three-dimensional space and asked to figure out the vector that would take us from A to B. Okay, so what we need to figure out is the horizontal change, the vertical change, and then the depth change that we would have for this vector. And you can do that by just making a comparison between your x's, your y's, and your z's. Okay, so 8 and 4, the difference between those, like to go from 8 to 4, because that's the direction here, to go from 8 to 4, you would have to subtract 4. Of course, that difference is going to get squared, so you can just take the absolute value of the difference, which means that we're going to use 4 and square that. For the y values, the difference between these, if we were moving along the vector, would be plus 2. But the difference between these overall is going to be 2. Okay, so we don't need to worry about negatives here, or positives. Okay, so we don't need to worry about negatives or positives here. Okay, and then for the z's, the difference is going to be 4. So that would be forwards 4 or plus 4, but we'll just write it as 4 regardless. All right, so if we add all that up and we square root it, that will be the magnitude of this vector. Okay, so we've got 16, we've got 4, we've also got another 16, which is going to end up being 36. 16 plus 16 is 32, plus 4 is going to give you 36. The square root of 36 is 6. That would be your magnitude. The magnitude of vector AB is going to be equal to 6. Most cases will probably not turn out to be whole values. Might need to leave them in radicals or round those off to decimals, but in this case, it did work out. All right, example 2, we're given 2 vectors. Vector U, which is going to go to the right 7, up 8, and then backwards 1. We've got vector V, which is going to be right 3, down 2, and forwards 2. Okay, and then we're asked to figure out all these little calculations. Just because we're in three-dimensional space does not mean that it's going to really change how we approach doing these problems if they were in two-dimensional space. Okay, so U plus 2V, what we'll want to do is double up the components in V, then go ahead and add those to the components in U. Okay, so your first component is going to be a 7 plus 2 times 3, so 7 plus 6, which will give you 13. Your next component, you're going to have 8 plus 2 times negative 2, so that'll be a negative 4, so 8 minus 4 is going to give you 4. Last, we've got negative 1 plus 2 times 2, that'd be 4, so you got negative 1 plus 4, which is not negative 3. You got negative 1 plus 4, which is positive 3. And that's the answer to that one. All right, V minus U, we're going to start with this vector, subtract the components that we have here. So we've got, let's see, we got 3 minus 7 is going to give you negative 4. We've got negative 2 minus 8 is going to be negative 10. We've got 2 minus a negative 1, which is actually 2 plus 1, so you get 3. All right, and then dot products. Dot products rules still apply here. What we're going to do is multiply our x's, multiply our y's, multiply our z's, and then take a sum. Okay, the answer here is still going to be a scalar value. It will not be a vector. Okay, so our x components will be 7 by 3. Your y components are going to be 8 times negative 2. Your z components are going to be, let's see, negative 1 times 2. Let me just verify I got all of them correctly matched. All right, everything seems to check out. So we got 21, then this will be a minus 16, and then we've got a minus 2 to follow that up. So really it's going to be 21 minus 18, which is going to equal 3. The dot product of U and V is 3. So what would be the dot product of V and U? Well, there's a commutative property here. It still applies. So the answer is still going to be 3. Right? The only difference here would be is that you would write it as 3 times 7, negative 2 times 8, 2 times negative 1. So all these would be flip-flopped, but the products are all going to be the same thing, which means that the sum is going to be the same thing. You have a commutative property. These two answers are going to be the same. And last, you can also figure out the angle between two vectors in three-dimensional space, which does have a lot of real-world applications when it comes to engineering. All right, so our vectors, 3 components for each. Okay, we're going to calculate the angle that's between them. The equation that we use for that is cosine theta, the angle that we're looking for, is going to be equal, we did not give these names, so I'm just going to call them U and V. It's going to be equal to the dot product of U and V divided by the product of the magnitudes of these two vectors. All right, so we let this part be for now, the cosine theta, and at the very end we'll do an arc cosine. All right, dot product, we're going to do 4 times 7. We're going to do negative 5 times 0. That's easy, that's a 0. You're going to do 3 times negative 1. That'd be negative 3. So we got 28, and we're going to subtract 3, which is going to give us 25. So there's your top. You got 25. All right, so to calculate the magnitude of the vectors, these are the components of the vectors. Okay, not to be mistaken in example 1 where we had coordinates and we had to figure out the distance between things here. Okay, so to get the magnitude of U, which I'm guess referring to that one as U, to get a magnitude of U, these are the values that you're going to square. So it's going to be the square root of 4 squared plus 5 squared. The negative will cancel itself out, plus 3 squared. Okay, the magnitude of V, so we'll let that be V, is going to be equal to the square root of 7 squared plus 0 squared, which of course does nothing, plus 1 squared. Okay, so we don't need to take any differences here. We actually had all our components. All right, for that, let's see, I'll go to the calculator just to make sure I type them all in correctly. Without the radical, we've got 16 plus 25 plus 9, which would give us 50. So square root 50. Same thing here, actually, that's going to be 49 and 1. So we get the square root of 50. That is going to work out pretty nice for this example. You won't always see this, but it's going to work out pretty nice because if the magnitudes of these are the same and they're both sitting within square roots, when you multiply these together, the radical actually just cancels out and you get 50. So we're looking at the cosine of theta is equal to 25 divided by 50, which of course is 1/2. So if the cosine of theta is equal to 1/2, then we already know, based off of our special angle measurements, that theta must equal 60 degrees. Okay, so you're not going to get that one happening all the time, but it did in this case. It turned out to be that.
Wait, what?